Hey there guys, how's it going? Mike coming back at you with another video on precalculus. In the previous video, we talked about rational functions. We talked about the domain of rational functions, asymptotes, which are important features of graphs of rational functions. How do we find these various types of asymptotes as well? In this video, we're going to talk about polynomial and rational inequalities. There are going to be a couple methods that you're going to learn as to how do you solve these particular types of problems. So to get things kicked off, what are polynomial inequalities? You may be able to guess, and your guess is probably right. A polynomial inequality is any inequality of one of the four forms below. Some polynomial f of x being greater than 0, less than 0, greater than or equal to 0, or less than or equal to 0. So one of those four options there. And the big question is, how do we solve polynomial inequalities? So here's the process that we're going to use to solve polynomial inequalities. You're going to be given some problem. First thing you want to do is move all the terms to one side of the inequality to write the problem in one of the four forms previously stated. Now, when you move all the terms onto one side, I highly recommend, I almost will force you to move terms so that the term containing the highest power of x after everything is moved has a positive coefficient. Don't leave a negative number in front of your highest power of x. Make your leading coefficient on your polynomial positive. So move things to one side or the other based on that. Once you have all of the terms onto one side, that polynomial is going to be referred to as f of x later on as we go through this process. So once you've moved all the terms onto one side and you have just the polynomial f of x, you're then going to set that polynomial equal to 0 and you're going to solve for x there. And the solution or solutions that you find are going to become the boundary points for the next step. You'll see how we're going to use those guys. But you want to take that polynomial that you have. For now, you set it equal to 0 and solve for x. Once you've done that and you found the x values that make your polynomial equal to 0, you're going to sketch the real number line and you're going to plot each of those x values, each of those boundary points that you found in step 2. And what that's going to do is it's going to take the entire real number line and it's going to break it up into intervals. Then, for each interval that you have, you're going to pick a test x value and you're going to plug it into your polynomial f of x. And you can note what the value you get out is, but really we're only concerned about whether the result you get is negative or positive. And the reason that we're only concerned about why it's negative or positive at one particular value is because whatever the function is at that test value, it's going to be the same for all other x values in that interval which you pick that test value in. So say you plug a number in and you got a positive result. For any other x value in that interval that's formed by two of your boundary points, or maybe just one boundary point, if you took any other number in there and plugged it into your polynomial f of x, you would also get a positive result. And then once you've done that, you're going to write the solution set, selecting the interval or intervals that satisfy the given problem. Now, as usual, this is going to make a hell of a lot more sense if we do a sample problem. So we are going to do a sample problem. And something like this is something that is very possible to see on a homework or quiz or on a test. Solve the following inequality, and then I give you a hint as to how a polynomial is factored. So the given problem is negative 10x cubed plus 12x squared is less than or equal to minus x to the fourth minus 40x plus 64. So step one, I want to move all the terms onto one side of this less than or equal to sign. And as I mentioned, move terms so that the highest power of x is going to have a positive number in front of it. Your leading coefficient is going to be positive. So to make that true, I'm going to move all the terms that are on my right-hand side over to my left-hand side. That will make that x to the fourth, which is the highest power of x, that's going to give us a positive coefficient. So what this turns into then is x to the fourth minus 10x cubed plus 12x squared plus 40x minus 64 is less than or equal to 0. And I put some stars next to this line because this line is very, very important. We are going to be coming back to this line right here when we write our solution set. This right here is our polynomial f of x. This is what we're going to be taking those test values and plugging those things into. We're also going to be setting this thing equal to 0 in the next step and solving for x. So, as I just mentioned, we want to take this thing, set it equal to 0, and solve for x. This is where the hint that I gave you at the beginning of the problem comes in handy. I would not expect you to factor x to the fourth minus 10x cubed plus 12x squared plus 40x minus 64 all on your own. I'm going to give you some hints as to what some of the factors are, and then you can carry on the work just a little bit more. So I have two quadratics here. I can factor each of these quadratics. X squared minus 10x plus 16 breaks down into the factors x minus 8 and x minus 2. And x squared minus 4 breaks down into the factors x minus 2 and x plus 2. So what are all the values of x that will make this thing equal to 0? Well, that's going to be negative 2, positive 2, and then positive 8. So these are the three boundary points that we're going to carry on into our next step. So we're going to sketch the real number line, plotting those boundary points, which we did here. And now we see that this gets broken up into 4 separate intervals or chunks. X values less than negative 2, x values between negative 2 and positive 2, x values between 2 and 8, and then x values greater than 8. So for each of these intervals, pick some x value in there, plug it into our function f of x, and note whether the result we get is negative or positive. It does not matter what x value you choose. You have free choice, so ideally choose something nice. Pick whole numbers if you can. So I'm going to pick some x value less than negative 2. I'm going to choose negative 3. If I take negative 3 and I plug it into my polynomial, I find that I get 275. That's a positive result, so I put a plus sign up here. All right, go to the next interval. Any number between negative 2 and positive 2, I'm going to go nice and easy. I'm going to go 0. When I plug 0 into my polynomial, I get negative 64. That is obviously a negative value, so I put a minus sign there. And now we keep doing the same thing for these other two intervals here. Pick any number between 2 and 8, plug it in. I chose 3, that gave me negative 25, so that's a minus there. And then pick any number greater than 8. I chose 10, that gets me 1,536, which is a positive number, so I put a plus sign there. So now we have this filled out, and we're going to go back to this important line here where I put my 2 stars. I want to know, when is this thing less than or equal to 0? So if I go back to my sign chart here, where is this function f negative or equal to 0? Well, it's equal to 0 at the boundary points of -2, +2, and +8. And it's also negative for x values between -2 and +2, or between +2 and +8. So the total solution set, the x values that make this polynomial less than or equal to 0, is every x value between and including -2 and +8. Note that we have the square brackets on these numbers is because we are including those endpoints. If we are not including the endpoints, we would not only have these be round brackets and not square, but we would also not have the value of +2 in there. So we'd have the union of 2 separate intervals going on there. So this is an example that we went through together to see how we solve a polynomial inequality. Try this guy on your own. I've again provided you with a hint as to how you would factor a polynomial that you may have to use in the course of solving this problem. Hint, hint, wink, wink. And see if you can come up with the solution set. So pause the video here, try the problem on your own. Once you think you have the answer, press play, and we'll see if you were right. All right, so let's see if you came up with the correct answer. First thing we want to do, move all the terms onto one side of the greater than sign. I kept the terms on the left as they were because the terms on the left contain that highest power of x, and the coefficient is already positive, so I don't want to mess with that. So now I have this long polynomial here is greater than 0. Again, this is our f of x. And note this guy. We're going to be using that at the very end. Now I'm going to take my polynomial, set it equal to 0, and solve for x. Well, I gave you what the polynomial factored down into, a couple quadratics, and then another linear factor here. X squared minus 7x plus 6 breaks down into the factors x minus 1 and x minus 6. X squared minus 9 is x plus 3 times x minus 3. And then we have our x minus 6 here. So the product of these 5 things is equal to 0. That means either one of these factors can be 0 on their own, which gives us 4 distinct x values: -3, +1, +3, and +6. Then we sketch the real number line, plotting those boundary points. It gets broken up into intervals. For each interval, we pick a test x value, and we note whether the result we got was either negative or positive. So I've plotted my boundary values. It's broken up into 5 separate pieces. For the first piece here, any x value less than -3, I took -4. I plug it into my polynomial f of x here, and I got -3500, so the minus sign goes there. Next, for any number between -3 and +1, I took 0, plugged it in, got +324, plus goes there. Then any number between 1 and 3, I chose 2, gave me a negative result. Any number between 3 and 6, I chose 4, that gave me a positive result. And then any number greater than 6, I chose 7, gave me a positive result as well. So now we're going to use our completed sign chart as well as our starred line right here to figure out what is the solution set. We want all the x values that make this thing strictly positive. Cannot equal 0, has to be strictly positive. So where do we see pluses happening? Here, here, and here. That is all x values strictly between -3 and +1. X values strictly between 3 and 6, as well as x values strictly greater than 6. So writing this solution set using interval notation in round brackets in parentheses, -3, 1, union 3, 6, union 6, positive infinity. Again, we're not putting square brackets on these. We're not including the endpoints because we would only include endpoints if it was greater than or equal to 0. But the problem, again, has strictly greater than 0. So we don't want to include the endpoints. That's why these are parentheses and not square brackets. So that is how we solve polynomial inequalities. We also have rational inequalities. You can probably guess, based on what we just did, a rational inequality is any inequality of one of the 4 forms below. Same kind of things, but now the function we're working with is a rational function. And the process that we use to solve rational inequalities is very, very similar to the process that we used for solving the polynomial ones, but there are some differences. There are a couple little things that you have to be sure that you do in a particular way so that you come up with all possible correct answers. To solve rational inequalities, first, you're going to move all terms to one side. That is the same as what we just did, but do not cross multiply. Typically, these rational inequalities are going to be given to you as some rational function is less than or greater than some constant. And some people are tempted to cross multiply. You do not want to cross multiply. You'll see why in a couple short steps. So do not cross multiply. Very, very, very important. Then, once you've moved all the terms to one side without cross multiplying, you're then going to simplify all the terms and turn the thing into one fraction. 2, you're going to find the x values that make the rational function equal to 0, similar to polynomial inequalities, but you're also going to find the x values that make the thing undefined. Now, for a little bit more clarity, the x values that make a rational function equal to 0 are the x values that make the numerator equal to 0. The x values that make a rational function undefined are the x values that make the denominator equal to 0. So when you find those x values, these x values are going to be your boundary points. From here on out, the process is the same thing as we did for polynomial inequalities. You're going to sketch that real number line. You're going to plot the boundary points. It's going to break the line up into intervals. For each interval, you're going to pick a test x value, plug it into your rational function f of x, and just note whether the result you get is negative or positive. And then you're going to write the solution set, selecting the intervals that satisfy the given problem. So let's do some sample problems here. So here's a rational inequality. Solve x plus 1 divided by x minus 3 is greater than 3. So again, I'm going to move all the terms onto one side. Typically, I would suggest just subtracting the constant from both sides. I would not suggest subtracting the rational function from both sides. So this is going to give me x plus 1 divided by x minus 3, and then minus 3. I want to change this all into one fraction. To get this into one fraction, I need a common denominator between the x minus 3, and we really just have a 1 here. So that common denominator is x minus 3. So multiply on the top and bottom here by x minus 3, as you see here. If we distribute that 3 in, and then we combine like terms, we are going to come up with negative 2x plus 10 all over x minus 3. And this thing has to be greater than 0. It has to be greater than 0 just as a result of the given problem. So this right here is that rational function f of x that we are going to be finding where it's equal to 0 and where it is not defined to find our boundary points. Then we're going to be taking values and substituting them into this thing here. So what x value or values makes this rational function equal to 0? To do that, set the numerator equal to 0 and solve for x. You find that x is equal to 5. The x value that makes this rational function undefined, take the bottom, set it equal to 0, and solve for x, and you find that x is equal to 3. So 3 and 5 are going to be the two boundary points that we are going to continue on with when we solve this problem. We have our real number line, plotted those boundary points of 3 and 5. The entire real number line gets broken up into 3 separate intervals. So pick a number less than 3 and plug it in, pick a number between 3 and 5 and plug it in, and then pick a number greater than 5 and plug it in. For a number less than 3, I chose 0. If you take 0 and plug it in for x here, you're going to get a negative 10/3. Then I chose 4 for this guy here. Plug that into f of x. You're going to get a positive 2. And then any number greater than 5, I chose 8. If you plug it in, you're going to get a negative 6/5. So we note the results here, where these things are negative or positive. We need to go back to our earlier work. We wanted to know where this rational function was strictly positive. So looking at our sign chart here, where do we see pluses happening? Oh, for x values between 3 and 5. And again, we're not including the endpoints because the question did not ask when is it greater than or equal to 0, just when is it greater than 0. So there's one sample problem. I have a second one on hand here. Try this guy on your own. Try to go through this same process and see if you can come up with the correct answer. Solve this rational inequality. 2x plus 1 divided by 3x minus 1 is greater than or equal to negative 2. So pause the video here, try to solve it on your own, and when you think you have the answer, press play, and we'll see if you are right. Okay, so let's see if you were correct in coming up with your answer. First thing I want to do, move that constant term over, get everything onto one side, and then we're going to turn the thing into one whole fraction. I added 2 onto both sides. I'm going to multiply on the top and bottom here by 3x minus 1. And then when you combine the numerators, you come up with 8x minus 1 in the top, and then 3x minus 1 on the bottom. I'll let you check that out on your own. So I want to know where this thing is greater than or equal to 0. This is my f of x. We need our boundary values. We need the x values that make this function equal to 0, as well as the values that make this thing undefined. Well, if we want to know where this thing is equal to 0, set the top equal to 0 and solve for x. That's going to give us x is equal to 1/8. To find where this thing is not defined, take the bottom and set it equal to 0 and solve for x. X is going to give us 1/3. So those are our two boundary values. I plotted these on the real number line. Any number less than 1/8, I chose 0, plugged it into f of x here, and that gave me a positive 1. So we put a plus there. Any number between 1/8 and 1/3, I chose 1/4. If you plug it into that rational function, you should have gotten a negative result. I got -4. That will vary slightly based on what number you chose. And then pick any number greater than 1/3. I chose 1. When you plug that in, I got 7/2, but you should get a positive result. We wanted to know when this thing was greater than or equal to 0. So we have pluses happening for x's less than 1/8 and for x's greater than 1/3. But since it can equal 0 as well, we want to include the 1/8, but we do not want to include the 1/3. And the reason that we do not want to include that 1/3 is because 1/3 made this function not defined. So we don't want to include that in there because that's not making it actually equal to 0. 1/8 does make it 0, so we do want to include 1/8, but we do not want to include 1/3. So when we write our solution set, it's going to be x values less than or equal to 1/8. I chose to write it as a decimal, which is 0.125, as well as all x values greater than 1/3. So 1/3, comma, positive infinity. So hopefully that is the answer that you came up with. Maybe some of you included the 1/3 just thinking about the greater than or equal to sign. Just maybe that was one thing that tripped you up. If that's the only thing that tripped you up, then you did pretty well. Ain't no shame in having one little error like that. So this is how we solve polynomial and rational inequalities. In the next video, we're going to begin chapter 4, and we're going to talk about a new type of function, specifically exponential functions. If you have any questions or comments, be sure to reach out to me, send me an email, have your friend send me a text, leave a letter in my mailbox, whatever you have to do. Otherwise, until the next video, take it easy, folks.